What do you think of when I ask you to imagine a continuous delivery organisation? Amazon? Netflix maybe? Google? Well, yes, those companies all practice continuous delivery. And I think that big web companies are what many people think of when asked that question. But in 2011, Mark Andreessen famously said, "Software's eating the world." So continuous delivery is not just for the web. Continuous delivery is an engineering approach to solving problems in software, maybe even more than just software. And it's of ever-growing importance in organisations of all different kinds. So what does continuous delivery look like outside of the big software companies on the web? How do you apply continuous delivery to building cars, for example? How did Tesla become the most valuable car company in the world? Tesla's application of software thinking to making cars has disrupted the car industry forever. So what does the Tesla software development process look like? Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't already, please hit subscribe, and if you enjoy the video, hit like too. Thanks first to our channel sponsors, Equal Experts and Harness. They are helping us to grow this channel, so please do check out their links in the description below. Also, check out my new book, Continuous Delivery Pipelines, which is, according to my marketing blurb, the essential handbook on how to build, use and improve your continuous delivery pipeline. And based on the feedback from our readers, lots of people seem to agree with my marketing blurb. In this episode, let's explore what continuous delivery looks like in a complex engineering environment. Tesla, according to their market capitalization value based on their stock price, is the most valuable car company in the world. They're valued today at around $800 billion. Just to put that into context, at the end of last year, when Tesla was valued at a mere $616 billion, Toyota was worth $194 billion, General Motors $62.7 and Volkswagen $96.4 billion. So the three of them don't add up to a Tesla. Tesla have done some important things. They've already achieved what Elon Musk said was widely quoted that was their goal when they began. That is to disrupt the car industry and make them take electric cars seriously. This is a great thing, and Tesla make great cars too. But more than that, in the 16 years that Tesla has existed, it has turned the car industry on its head. They've done this in part by applying software thinking to car manufacture. There's another unique part of the experience of buying a Tesla beyond just having a good car. If you buy the car, and it then gets better. Tesla is a continuous delivery company. Please notice, I didn't say that Tesla developed their software with continuous delivery, which they do, but that they are a continuous delivery company throughout. These ideas go deep into how Tesla approach the engineering and production for their cars across the board. They've built factories that can quickly be reconfigured, sometimes just through software, allowing them to build better parts when they think of an improvement. They take an aggressively lean approach to solving problems and to production. For example, they've pioneered a new way of casting the main structure of a car. They invented their own version of aluminium alloy and designed molds to optimize the flow of material through them so that the roughly 800 pounds of molten aluminium can fill the whole mold in milliseconds. This may sound crazy, but this change in approach has huge impacts on both the speed and quality of production. It reduced the part count for the body of a car from around 170 parts for a conventional car to 1 for a Tesla. And that meant that each chassis is identical to every other. They are so far ahead of their competition that industry experts don't believe that they can be caught. In 2015, Porsche announced that their concept EV sports car, a car that could do 0 to 60 miles in 2.5 seconds and would have a range of 300 plus miles, would be planned for release in 2020. 2020 wasn't a great year and that car isn't yet available. But meanwhile, the Tesla Model S could do 0 to 60 in 2.5 seconds and had over a 300-mile range in 2015 when Porsche announced the inception of their sports car. The range is significantly better than that for the Tesla Model S now. Oh, and it's a sedan, not a sports car. Car industry expert Sandy Munro says Tesla would have to do something horrific that would allow the rest of them to catch up. But even if they caught up, Tesla's going to move ahead. And when they move ahead, they're going to leave everyone behind again. They are ahead in manufacturing techniques. They're ahead on electronics, battery technology. Who's going to catch up? So what has all this got to do with software? Well, a modern car, and most definitely a Tesla, is a complex distributed computing platform. Depending on what you count, there are around 100 different computing devices in a modern Tesla. Many of these are discrete electronic control units, ECUs. These communicate with each other via an in-car network. If it helps, you can think of these as discrete services spread around the car. But more than this, Tesla embody the philosophies that I think are the underpinnings of continuous delivery. A scientifically rational engineering focus and a lean-inspired approach to continuous improvement. Tesla take continuous delivery very seriously. For example, it's mentioned in virtually every technical job advert that I've looked at. They use lots of ideas and even technologies that viewers of this channel would think of as familiar. They take a BDD approach to testing, for example, and they value excellent interpersonal communication skills for engineering roles alongside experience with Docker and Kubernetes and working knowledge of continuous deployment, feature toggles, logging metrics, and so on. Tesla have established sophisticated deployment pipelines around the development of individual ECUs. Developers commit a change and that is built and evaluated quickly, with compilation, unit tests, static analysis and a series of integration tests. These are organised to give fast, efficient feedback to the development team. They've taken the approach of replicating the dependency structure in the system as dependencies in their deployment pipelines. So a change to some shared code will, after local testing, be promoted to dependent systems and trigger a run of downstream pipelines. This is a common strategy in big systems. I have to confess that I think that there are some other options for optimizing systems like this that can be a little more efficient, but I guess that Tesla really do know what they're doing. The real test of the effectiveness of this approach and any other is how often breakages propagate downstream and how long it takes to recover from the breakages when they do. If this testing all passes, the change will be packaged and then promoted to integration testing. I'd call this the end of the commit stage. At this point, Tesla have a fully functional container that can be flashed to any compatible hardware. The embedded device equivalent of a Docker image, perhaps, a release candidate. Next comes integration testing. I'd probably refer to this in my terminology as acceptance testing, and this is again per ECU. It takes two forms, open loop and hardware in the loop testing. These are common ideas in testing embedded systems. Open loop means abstract tests of the system, invoking one behavior at a time to see if it does what you expect. Hardware in the loop means a more sophisticated simulation of the hardware, with simulators recreating the exact signals that the device would see in real use. There's often a debate about the merits of open loop versus hardware in the loop testing in embedded development organizations. I think there are some architectural choices that you can make that improve the relevance of the simpler open loop tests, but Tesla duck that debate and do both. The ECUs communicate often through industry standard or at least well-known and so presumably fairly stable protocols. So there is tooling available that can be used to simulate interactions with the ECUs. If all the ECU testing passes, then the binary ECU image, the release candidate, is promoted. It's committed then to a binary ECU repository, and this commit triggers a new second stage deployment pipeline. This pipeline is designed to evaluate related clusters of ECUs together. This testing is mostly hardware in the loop acceptance testing, and Tesla are quoted as running tens of thousands of these tests for a whole car. I confess I was slightly surprised. I expected that it would probably be more than that. We ran tens of thousands of tests when building a financial exchange, and a car's probably more complex than that. So my guess, and it is only a guess, is that each of these tests is pretty big and complex. I don't have any information on how Tesla integrate testing into their development approach, but it would be fascinating to find out. Tesla employ what I call a test avoidance approach as part of their pipelines. They analyse the changes to see which tests they don't need to run, and only run the tests that are related to a particular change. These tests are run in parallel with each other on a test farm, with lots of different hardware configurations available on the test farm to support different kinds of tests. One of the things that they do to support this is to use a centralised test distribution system that can match the needs of a particular test with the hardware needed to host that test and at test runtime. I've done something similar in the past, tagging test cases and then dynamically allocating and load balancing them across a test grid. In addition to all of these functional tests, there are a series of safety tests that are also carried out. And once all of these tests have passed, there's a level of manual testing that is demanded by regulation, testing a car on a test track and putting it through its paces. I assume that because of the quality of the rest of the process, this is largely a rubber stamp exercise, necessary for regulatory approval, but one that rarely, if ever, finds a problem. That is the best way to cope with a process that enforces such delays, because errors found at this point would be more painful to fix than found if they were found earlier. So really focusing on quality upstream will minimise the chances and so the impact of a failure at this point. Tesla then deploy changes to customers' cars over the 4G wireless phone network. They roll out changes across the fleet of cars incrementally, upgrading hundreds of cars per day. I would guess that they monitor this rollout quite closely as it progresses and would stop the release of anything that appeared problematic. Canary releasing for cars, in fact. I got a lot of the information on the development process in this episode from a paper written by Sebastian Vost, so thank you, Sebastian. If you'd like to read it, there's a link in the description below. Tesla have adopted the philosophy of continuous delivery and applied it to cars. They've become so effective at releasing software changes and to their customers that they've become acclimatized to the stream of improvements. So acclimatized that a few customers have even complained when they didn't get hardware upgrades for free too. There's just no pleasing some people. Deeper than that, their application of engineering principles and lean thinking mean that they have disrupted the car industry. The combination of taking an innovative, experimental approach to solving problems and a rigorous engineering approach to controlling the variables is at the heart of what I think of as continuous delivery. And the reason why I think that it's both applicable and important, whatever the nature of the software that you're creating, or hardware for that matter. If you have enjoyed this episode and would like to see more case studies like this, do let me know in the comments. Thank you very much for watching.